Hello, everyone. David Alfred Ostrowski here. And in this recording, I'm going to be expanding on my theory of computation lectures. I'm going to be talking about the halting problem specifically. I would encourage you to get the appropriate premise for this, to listen to my limits of computation lecture before this. I think it would help. And this is an extension of that. So if you didn't get a chance to see that, take a look at it or review the appropriate literature online. I am loosely following the Linz, L-I-N-Z, text seminal book on theory of computation. Okay, I'm kind of putting my own word of mouth explanation. In my last lecture, I talked about the limits of computation. This is the essence of computer science, is essence for everything that we do for the most part as a computer scientist. Okay, that's why we use artificial intelligence. This is why you may be questioning, okay, if technology such as AI is going to take over the world, okay, and so on and so forth. I don't want to elaborate on that. I got other commentary videos that might touch off on some of those topics. Here I want to talk about the halting problem, okay. You start off with the idea that there are more languages than machines, okay, and the halting problem takes this in similar format, puts it in a more very proof by refutation. We assume that exists, and then by virtue we have to assume that we made the wrong assumption, right? That we come into that logical conclusion. So again, if you don't feel good about understanding the basics of countability, decidability, and the overall limits, and the fact that there are provably more machines than languages than machines to solve them, okay, which could be even translated, there's more problems than can be solved by a computer, okay, then you might want to review the earlier material, because that will definitely help this make more sense to you, okay? So let's continue on here. We're building on that premise. We're building on the concept of the Chomsky hierarchy. As we start to look in the finer categories of recursively enumerative languages, we have context-sensitive recursive, and then finally, the largest, most broadest category is recursively enumerative. Okay, this touches off on this point that I have a specific behavior with a machine. Okay, and let's create a machine. I could perhaps call it a universal Turing machine. Okay, it's going to be a machine that's going to take in a Turing machine and a word on that machine. Consider it a language tester, okay. And it's going to have some type of output. You call it a program tester for that matter, right? Remember, everything we talk about languages and applications, there's really not much of a distinction between them. Think about how our APIs solve problems that used to be applications that get rolled in an API. So what's the difference? Okay, not much, if at any. I can have this machine, I can take a Turing machine and an associated word on that, just as we did this manually when we looked at these other examples. And either can be an accept, okay? Pardon my writing here on the tablet here. A reject, okay. These are the easy languages, but in the real world, what happens, okay? And as we get into the distinction between recursive and recursively enumerative, and I may take out some time to create more content to get a little bit deeper in an understanding of those, okay? We have a third option here, and that is loop, okay? No response, thinking, okay? No answer. Thinking about it, still working. Okay. What does this mean? It may mean it accepts it or rejects it, but we just don't know. Maybe it needs a couple extra seconds to run and it will tell us the answer. Maybe it needs 5 more hours to run. Maybe it needs 5 centuries to run. Maybe it needs, if you look at the exponential growth of equations, let's say we're trying to brute force chess, which all the moves together is greater than the number of molecules in the known universe. Okay. Let's say I'm going to solve a problem like this. This is an incomprehensible amount of time, numbers, whatever. Okay. We just don't know. We don't know what's going on in this capacity. Okay. So what we need to do to address this type of situation is we consider the fact that, well, let's consider there's a language that there is a possibility that I can create a halting machine, okay? And this, I can call this as H, and this will take input, similar input as the last Turing machine and associated word, except this has a yes or no. And the reason I'm saying yes or no doesn't mean it accepts or rejects. It's not going to define that. It's going to say, yes, it halts. And it might mean it determines that it's in language, it halted in a determined language, or it determined that it is in language, or it halted and determined that it isn't in language. But at least we know. The second answer is definitively is that does not halt. Don't confuse the two. Don't confuse this with reject. It's not the same. And some descriptions of this concept of the halting machine doesn't draw as deep of a distinction between that. So it can be a little bit confusing and you might miss the point. So dwell on the fact that the halting machine, the component of the halting problem, okay, the term is H, that's like that hypothetical language that solves all languages that may exist that we may not know about, okay, uncountable. I'm assuming in this case that it exists. I can define whether it halts or it doesn't halt, okay? And this is the start. This is our beginning assumption, okay? If this is true, then we can define a machine to solve anything, okay? Then computers can solve everything. Let's assume it is true, okay? In similar nature, similar thought process that we did with pumping lemma for regular language, pumping lemma for, we assumed that our language was solvable, okay, to some extent. Okay, so let's continue that thought. I'm going to wipe this clean slate here, okay, to get some more real estate here. So I got this halting machine, okay, and I'm going to make that a part of a bigger component, right? I am going to put this in here, and there's my halting machine. And it's going to say, yes, it halts, or no, it doesn't halt. Takes my input, right? It's my assumption this exists. Larger machine, let's just call it M, just for simplicity. All right. So what can I do with this? If it halts, I know I can I put a program in an endless loop? Of course I can. Give me a language. I'll give you a while statement, while true, whatever. That's going to put me in is that ever going to complete? No. Okay. And I can put the functional equivalent in any Rust, Python, PHP, Slitty, anything. I can put in some kind of loop like that, right? So I can put my program into an endless loop. And I can make that part of the bigger machine. So what happens here is we are constructing a scenario that's going to support our conclusion. I take an input of a machine and an associated word, I put it into my halting machine. It's going to say it halts or doesn't halt. Didn't solve whether it accept or reject. The bigger question here is that machine going to halt or not? That's the bigger problem. Doesn't matter whether it is accepted or not accepted. That's the definition of our language, understanding. So we've gone all along with the languages in the Chomsky hierarchy. The bigger question is, can I run it for a few more minutes? Is it eventually going to complete and give me the truth? Or is it just keep running forever? Okay. But in this case, if it does halt, I can put it in a loop. And it keeps on running forever. And if it doesn't halt, then I leave it the same. Okay, so that's the premise of that machine. So I can take M and I can actually feed this with M prime. I can take itself and feed that into my own machine. I can take a copy of this machine as it exists and feed his own input, right? After all, I'm feeding in a machine and a word that operates on a machine. So there's nothing that says that I can't take itself. If I have a program that tests programs, I could use that program itself as input to itself. Well, certainly, there's no reason I couldn't. But here's the problem. If I feed that in as input, if it halts, it doesn't halt. And if it doesn't halt, it halts. Machine, the M prime that's being fed in, it's got one or two results. And don't get hung up too much on the details, might hurt your head a little bit, right? But it's either going to halt or not halt. There's no other option. But if I feed it into this machine, feed itself as input, when it halts, it's not going to halt. And when it doesn't halt, it halts. That is paradoxical. That's impossible. It can't halt if it doesn't halt, and doesn't halt if it halts. It's one can't be zero, zero can't be one, right? It can only be one or the other. Therefore, I made this can't exist. This machine M is impossible, okay? By this example, okay? I know I can do this. Somehow in its design, I made a mistake. I made a wrong assumption. The only thing I have left is to assume that I cannot create a halting machine. I can't do this by this proof. Remember, if I could define a language that can't be defined, that in and of itself is impossible, right? So I have to use a proof by contradiction, or I draw an assumption, I assume it to be true. But this, by what I just proved, cannot be true. Therefore, there exists problems that cannot be solved by a machine. No story. Hope this helps. Thanks for listening. Take care. Talk to you soon. All right. Bye now.